scheduled more perfectly than it is after Danny's talk and after a couple other talks, including Elizabeth's and a couple of talks from yesterday, because I'll give you basically some kind of preview or review of what do we do with sea ice models and those improvements and how we put them into coupled model simulations with focus on the Arctic Ocean. So I wanted to acknowledge my colleagues, Robert Osinski from Institute of Oceanology in Polish Academy of Sciences, Andrew Roberts, Sami Kamal, Young-Ju Lee from NPS, and there's a larger RASM team, Regional Arctic System Model team, which depending how you count is somewhere about 15 to 20 people total. And I wanted to acknowledge support from various agencies as well as the computational resources that are being provided by the Department of Defense High Performance Computing Modernization Program. So in terms of what this talk is about, I'll give you some example, at least in my opinion, top examples of big problems in the Arctic. And then I'll give you a few more examples how SIPW01 are dealing with related problems to that. And then I'll bring up our regional Arctic system model. I'll provide some overview, show you some selected results. But then I'll talk about how results in RASM change or sensitive to different processes that resolve different mode configuration, spatial temporal resolution, and sensitivity to changing parameter space. And what I have in mind by saying changing parameter space is if you go from a model resolution 100 kilometer to a model resolution 10 or 1 kilometer, you have to change your parameter space because otherwise you're just trying to represent something that was tuned for a coarse resolution model with a high resolution simulation. And so this would be a major part of the talk. I'll give you just a brief summary of our first 2 years attempts at using RASM for predicting the sea ice, September sea ice extent in the Arctic as a contribution to the Sea Ice Outlook community effort, and then I'll conclude. So big problems. First problem is the surface radiation budget in the Arctic. And if you follow those bullets here, the Earth radiation budget is, if it's in equilibrium, it means that absorbed solar radiation is balanced by outgoing long-wave radiation. If you define something called Earth energy imbalance, which means that this balance is not satisfied on a particular time frame, basically those are perturbations of this budget up here, manifested by radiative flux imbalance at the top of the atmosphere. Okay. Now, if you take the absolute mean in the global sense over long term, Earth energy imbalance is on the order of 0.5 to 1 watts per square meter. And that metric basically is a definition of a global warming for some communities at least. Okay. 92% of that imbalance, on whatever time scales we're measuring, is actually accounted in the ocean by oceanic heat content, 4% by land sea ice, and then 3% by land atmosphere. Okay. Now, if you look at the polar ocean and look at the shelf regions, marginal seas, and deep ocean greater than 2,000 meters, the main source of our uncertainty are in the oceanic heat content. If you look at the SIPW01 or state-of-the-art climate simulations, representation of the upper ocean hydrography, deep ocean hydrography, and resulting oceanic heat content is actually widely varying and commonly incorrect compared to whatever observations we have. And actually there's a nice publication by Van Schuckman in the Nature Climate Change last year. Now, a paper by Mark Cerezo from about a decade ago for winter time, he didn't define this as Earth energy imbalance, but that was basically trying to balance the outgoing energy. Basically, look at this. We have roughly 35 watts per square meter imbalance during the winter time in the Arctic, compared to a global long-term average of about 0.5 and 1 watts per square meter. So there's a huge uncertainty in terms of energy budget, surface energy budget in the Arctic that needs to be improved in order to for us to take advantage of our state-of-the-art climate models and state-of-the-art sea ice models. Another big problem is the momentum transfer. Okay, and Danny had already discussed the issue of the form drag and parameterization of form drag in the new sea ice model. If we cannot transfer momentum from the atmosphere through sea ice to the ocean, this is the second big problem that we have in terms of communicating energy from across this interface, okay? So I wanted to notice is that if we have some form of stress, which is a function of the, it's not just the ocean velocity, it's a difference between ice and ocean velocity. And you somehow start increasing the velocity for a drift of sea ice, which has been documented, one of them being paper by Pierre and Paul, it means that you increase the ice-ocean stress. Now, if you look at the equation, I believe this is from McPhee's paper, for the up or downward heat flux to the top of the ocean or downward, it depends on the various parameters, density, heat capacity, but also on something called friction velocity. And the friction velocity is defined as the square root, a power of half of absolute value of stress divided by density. So if your stress is increasing, your friction velocity is increasing, that means that your heat fluxes up and down are increasing, which means that if you have increased the drift of ice, you have increased the stress of ice-ocean, which means that you provide more mixing to the ocean. And if you happen to have some heat stored below the mixed layer in that ocean, that means that you will be bringing that heat to the bottom of the ice, regardless of the time of when that happens. So now a few examples how well the state-of-the-art SIMIP5 suite family is representing the ice in the Arctic. And this is from a paper several years ago, but we basically look at SIMIP5 for a first 5 years in 2000. So basically kind of like going into this new regime of sea ice where the ice has significantly thinned and started being reduced extent. If you look at the upper left here, four models, basically there's no skill in terms of representing the ice thickness distribution at all. And then you have look at some other models down below here, and what you can notice actually that they have thicker ice in the Western Arctic than in the Eastern Arctic. And this one here is kind of like let's say reanalysis based on the ice-ocean model force with the atmospheric reanalysis. One of our earlier model results that it's comparing well with whatever available observations from the remote sensing and the submarines. So you have ice, thick ice around north of Greenland and Aegean Archipelago, and thinning outward towards the central Arctic and towards the marginal seas. So for example, if you look at this kind of model, it has very thick ice on the western side and much thinner ice in the eastern side. So what it means is that might be different processes might be involved in that model compared to that model or to those models that are significant to be understood before we start to making sense about scale of those models. And as an example of those processes, I wanted to emphasize that if you look at the annual cycle of the trends in the Arctic sea ice decline with regard to ice extent or concentration, there are different regions and different seasons that are significantly changing or accelerating the ice decline. During the March time, decline of ice is taking place in the marginal seas, with exception of the Bering Sea that for some reason has been actually increasing. During the summertime, actually is the Western Arctic and the Siberian seas that experienced at most decline, and maybe something along the continental slope of the Eastern Arctic as well. So if you represent the decline of sea ice cover in the summer on the eastern side in your model, it's not correct, even though you might have the correct estimate of your total ice extent for that September, or the mean September, or the trends. So one other thing is that if you look at the SIMI5 models, and we're actually referring to reanalysis, European reanalysis ERA 40, the earlier version, mean sea level pressure difference between the SIMI5 in winter, December, January, February, minus that from reanalysis, you can see that there are significant biases. This model in particular basically doesn't have the buffer gyre or buffer high. Some models actually have a very significant biases on the positive side, and many other models are somewhere in between. So now if you think about the wind driving the sea ice distribution and the ice dynamics, if you don't have the major features of the atmospheric circulation in those climate models, how do you expect to have the ice cover and especially ice thickness distribution represented realistically? So with that introduction, basically I wanted to provide a reason why we have decided some 10 years ago to start working on this regional Arctic system model for many reasons. One reason is that if you have a global model, you have to worry about many different regions, and Arctic might not be necessarily one on the top priority list. If you focus on the Arctic with a regional model, you have all the resources all the time and all the people looking at that particular region. Second thing is that if you do a regional domain compared to the global domain, you can focus your computational resources on that domain, meaning that you can provide higher resolution compared to the global models for the same amount of resources. And if you have access to the DoD computers, you can actually allocate even more. Okay. And the other thing is that if you have a high resolution, you can hope to start resolving some processes. And our approach is a process at the time. Let's try to understand one process, see whether we can improve that process representation or simulation in a model and see its effect. Find out what the effects of it. So there's a lot of processes that are underrepresented or basically missing in global climate models, including the latest versions of the climate models. One of them already shown example is the sea ice thickness distribution. Sea ice deformation, when you have a very coarse resolution, even if you have a very good model, sea ice model, you won't have those deformations that are actually occurring observed from remote sensing, for example. Export of ice, representation of fast ice that has been mentioned already, snow cover distribution and its effect from the albedo point of view, a radiative balance, and then melt points that have been discussed, and surface albedo. Now, the sea ice on its own can determine a lot of those parameters and a lot of those exchanges and contributes to the budget. But as Danny very nicely mentioned, you need to have a realistic representation from the top and from the bottom bundle layers that are attached to the sea ice and somehow affecting or forcing the sea ice. So one important thing from the ocean point of view is that the global climate models are not really resolving, and eddies are our primary means of distributing and dissipating the large-scale energy. So we need to understand their role in the Arctic. Tides are important to some latitudes as well. Representation of the surface mix layer in contact with the ice, floating ice on top of it. And now the circulation in terms of buoyancy-driven coastal current, boundary currents, distributing the property, heat, salt, fresh water that contribute to the upper ocean heat content and so forth. And then from the atmospheric point of view, we need to, in our model, to be able to represent the large-scale atmospheric circulation pattern, such as the Arctic oscillation, such as Pacific decadal oscillation, and many others, those large-scale patterns that have been defined and demonstrated based on observations. Of course, clouds, from the radiation point of view, it's like the 1,000-pound gorilla. If you don't get clouds right, you don't get the radiation. But this is not the only problem for the polar region or for the Arctic. Clouds are the main challenge for the atmospheric climate models to represent. And we're far, far away from cloud resolving models. Distribution of aerosols and their contribution to radiative exchanges, and then atmospheric fronts and so forth. And in terms of the interactions or feedbacks, exchanges between the shelf and basin, deep basin in the ocean, are very important, and there is a basically kind of dynamical barrier that it's not easily crossed by the currents and water flow if you don't have the means to do that. Wave ice interaction we've heard before, air sea ice interactions, and coupling of all these different components are very important. In here, I'm focusing basically on processing and coupling that are of relevance to the Arctic sea ice state, and then we'll also talk about sensitivity to parameter space of this sea ice, Arctic sea ice state. So the RASM domain are shown here. The inner shaded domain is the ice and ocean domain. Commonly or by default, it's a 112 degree or 9 kilometer rotated coordinate system. So basically very uniform 9-kilometer resolution in this shaded, color shaded domain. And then we have the land and atmosphere encompassing that domain, limited by the red box for the atmosphere and land. And then we provide a surface boundary condition with the extended ocean, which is basically from annual climatology. In terms of some specific details, the atmosphere by default is 50 kilometer and for the levels. Land has the same grid, horizontal grid, and have 3 soil layers. Ocean is 112 degree at 9 kilometer. We also have a higher model configuration at 148, mostly to look into the effects of eddies being resolved, at least to some degree, in the deep basin in the Arctic and its importance. And we've also played around with the vertical resolution, specifically increasing the upper ocean resolution by additional 15 layers in the top 100 meters of the Arctic Ocean. The sea ice model is the sea ice 5, and we also have the column package version already implemented and tested. And we have the same grid as for the ocean. So 112 degrees, about a 9 kilometer. For the 148, we're not necessarily focusing on the sea ice results because there's an issues in terms of the violating some basic physics assumptions there. But the ice thickness distribution, it's 5 categories like Elizabeth was talking about. We have tried, and I'll show you results from 2 different rheology options. The one that Danny was talking about, elastic and isotropic plastic, and the default being elastic viscoplastic rheology. And a very important aspect also is that we have a very high resolution temporal in the model. Our coupling time step in the 9 kilometer ice ocean, 50 kilometer atmosphere land is 20 minutes, and for those higher red configuration, it's 10 minutes. This is important in terms of representing or resolving some of the critical processes in temporal space that might be of relevance in the Arctic. One of them may be inertial oscillations that are related to passing storms and so forth. So this is a schematic diagram of the model. We have the atmosphere, sea ice model component, ocean, and land. We have the routing scheme for river from land to be routed to the ocean. And we also have the marine biogeochemistry, working with colleagues at Los Alamos to basically test what they have developed and tested in their model configuration in a fully coupled regional high-resolution model configuration in terms of the effect of physics and representation of biology in the high-resolution model configuration. In addition, we also are working, there's a project we're working on the fjord module, but that's not necessarily of relevance here, with an exception that in a fjord, representing the sea ice as a part of the fjord system, it's a long way out there challenge that not many people even are thinking about. So the idea is that if we can develop the fjord module that will represent the non-hydrostatic 100 meter resolution in the fjord interaction with the glacial termini and so forth, we still need to somehow put some sea ice model on top of it, and there's no sea ice model that is available for that reason. Okay, so some results. This is basically trying to look at the climatology, winter maximums, summer minimum, run with the forced reanalysis. So we're running basically ice-ocean subset of the RASM with prescribed reanalysis to find out whether we can compare to remote sensing satellite observations with the green contour here. This is the mean remote satellite observations for March and September 79, 99, and you can see that actually quite well representing the annual variability from winter to summer with this model when prescribed with the realistic atmospheric forcing. The bottom panel is showing time series of the ice extent anomaly here. The red is the model simulation, and the black is the same way calculated the anomaly of the ice extent from the remote sensing from passive microwave. So you can see that with the atmospheric forcing prescribed, we have those variability that are quite similar to variability, intraannual variability from observation, and then we have trends, and we also represent some of the minima in the recent years. Now, if you look at the specific simulation, specific cases, 85 is my favorite year for having a thick ice. And we're showing here March and September 85 on the left, and March and September 2007 on the right. So this is basically heavy ice here. This is the light ice here. The color shading represents the ice thickness distribution. And then we also show a specific ice extent from satellite, from passive microwave for that particular year and that particular month. So you can see that after some tuning of the parameter space, roughly about 50 simulations, we can tune the model to represent March of 85 or September of 85, and then when we go with the same simulation to September, March 2007 or September 2007, we captured that variability quite well, okay? But that requires a lot of effort, and actually that becomes even more difficult or challenging as we go to the fully coupled simulation, because they are much more expensive. So part of the reason we're doing here with the forced simulations with prescribed atmosphere is that the cost of running 50 simulations is much less compared to running the same 50 simulations with the fully coupled model. However, one comment to make here right away is that if we go to the coupled model with some of the optimal configuration from the forced case, that doesn't apply, doesn't work, doesn't produce optimal result for the coupled simulations. So there's a caveat there. Now, a very important aspect here, we can run those number of different experiments shown here by different color lines. So we have here 5 experiments, and we're comparing total ice extent from those experiments. And as you can see, there's not much variability. There's a little bit in the maximum, maybe a little bit in the minimum, but overall, looks like those varying experiments are representing very similar ice extent over that time period. Now, if we look at the same color coding for those experiments and we plot the time series of volume, the story is quite different. Actually, the difference between the red experiment here and the purple experiment is roughly twice much volume for the same amount of ice extent. So there's 2 comments here. One is that the ice thickness and ice volume is much more sensitive in those simulations to varying parameter space than ice extent. The other conclusion is that if we're using ice extent as a measure scale of the climate model simulations, we're way out, possibly way out in terms of representing thickness and the volume.
What are the parameters you're playing with?
I can talk about this offline, I guess, but we've tried a lot of different things. Some of them are specifically within the CI, such as ice strength or the equivalent ice strength parameter. And some of them are related to coupling in terms of how much momentum is being transferred between the ice ocean and the atmosphere as well. We try to stay away from playing with albedo because, as Elizabeth stated, we kind of believe that albedo is more or less correct, and we don't want to use albedo to tune the model simulations. But anyway, here's the case, mean September for the red case, and mean September for the purple case between the 2 results. And the green contour here still represents the mean September for those years from observation. So you can see that for the wrong solution in terms of thickness volume, we still have a very good agreement on the ice extent between the purple and the blue case.
Just remind me, it's with the free atmosphere. It's not forced atmosphere.
This is forced atmosphere. This is G case. This is reanalysis. Yeah, there's no feedback. There's no coupling back. It's only one way. Yeah, so that's even stronger sensitivity than you would have with the atmospheric state varying between those 2 simulations.
My guess is that the ice extent would vary much more in coupled mode. Here you force the location of the ice edge because the reanalysis simulates ice concentration. I guess that's part of it.
Yeah, if you have realistic winds and realistic atmospheric forcing, you expect to have more realistic results. If your atmospheric model goes so far away in the Arctic from reanalysis fields, then definitely you will not have the same agreement with the ice simulation based on this atmospheric forcing with the coupled model. But anyway, another thing that we did is just we looked at the effect of changing rheology, EAP being in red here and the EVP being in purple, I guess. And it's exactly the same simulation. There's nothing different between, that's a fully coupled model run. Then we just turn option 1 for EVP and option 2 for EAP. So you can see that actually a significant change once you remove the spin-up time that adjustment to the different rheology, but basically about 27% more ice volume with the EAP compared to EVP. That doesn't mean that it's better. We're actually still debating, especially with Andrew and a couple other colleagues, that we cannot demonstrate that the EAP has, with whatever comparison of the observations for ice thickness, produces a more realistic ice thickness. But clearly it's producing more ice. It's producing more ice in terms of a fully coupled simulation. And one important thing to note is that in our case, we have 27% more ice with EAP for fully coupled, but roughly only half of that difference for the force simulation. Okay, so now the other thing is that I don't know whether this is multi-scale or not. I think that it could qualify as a multi-scale. If you expand the model from a force model simulation to a fully coupled model simulation, you actually will see a different sensitivity and different model scale as well. So where is this coming from? Okay, and Danny already has alluded to this, but basically if you compare, you can separate the total ice volume or total ice thickness into level ice and the deformed ice. So the level ice is shown here by the dashed lines here. So the blue or purple dashed line and the red are very similar to each other. Actually, if you compare them, they're 6,500 versus 6,000 kilometers, okay? So level ice is almost the same, roughly 7% or so, 8% different between the EAP and EVP rheology. 41% difference is related to the deformed ice. So basically the difference in the ice volume is from ice deformations that are, as Danny has already suggested, they're more frequent and better representing the deformations in the long-term simulation and climate model. So by producing more deformations, you produce more ice eventually, and then ends up getting that volume increase. So that there is a question here: where's this thickness or volume coming from? And we looked at our standard model results, which is monthly mean ice fields, and we couldn't see the difference in deformation fields. I don't have time to show that, but basically what we did was we started looking at a particular month and a year, comparing deformations in one rheology with a different rheology, and as a matter of fact, in the monthly means and even daily means, the EVP was suggesting there's more deformations than EAP. However, once we went into the sub-daily scales, time scales, the difference between the EAP and EVP came clearly very positive. So at sub-daily scale, if you integrate 24 hours of this variability, which is just the difference between the two rheology hourly, subtracting the daily from the actual daily deformations, you can see that actually this possibly on the daily, then monthly, and accumulated scales can contribute, as Ron Kwok suggested, about 20% to the total ice growth with the over 6 months time period. Okay, so the issue here is that very seldom people have produced an access to sub-daily model output. But there is an information there that might be actually quite important from the point of view is that if you want to understand the difference in rheology, and you will do some kind of like a comparison of the deformation fields, you will not be able to explain why you have the difference in the ice volume. Another aspect that I already mentioned briefly is the temporal scale, and this is results from Andrew's paper, Roberts et al. In Annals of Glaciology. I forgot to put the reference here, but basically what Andrew did is just if you run a simulation with the high frequency coupling in the ice ocean atmosphere model simulation, you get the inertial peak in the ice drift power spectrum. If you don't, which is for example, this is the CSM without representing the resolving the temporal scale here, you clearly don't have that power spectrum peak at the inertial time scale. Why this is important? If you have storms frequently passing across the Arctic and you start moving ice at those inertial oscillations, the momentum is transferred into the Arctic surface upper ocean, and if you have some mixing and happen to have some heat stored in that ocean in the Arctic, you will enhance the oceanic mixing and entrainment of heat to the bottom of the ice, which will contribute to the bottom melt and preconditioning for summer melt for the large scale. Now, in terms of deformations, if you look at this is just a monthly area and ice drift from the size model at 9 kilometers. And now you look at the divergence field here for that particular month. And then you look at the fuzzy ice formation and resulting surface heat fluxes, which are shown here by those more warmer colors here, yellow, orange, and red. They are related to those deformation fields in terms of the ice divergence. And as the fuzzy ice is growing, it has followed the removal of the surface heat. And if you look at the numbers, those are very small regions or linear kinematic features, but you can get easily into tens of watts per square meter from a deformation event like this. So if you go and look at the storm event, this is the EAP results here shown. And we're looking at a storm that came up after January 20, sometime in 1980. By the 23rd, 3 days later, you can see that the ice is deforming in the southwestern Beaufort Sea and Achakchi. The storm is moving, so some of the deformation linear kinematic features are closing already. 7 days later, the storm is gone. Okay. Now, if you look at the fuzzy ice formation, clearly we have formed for some fuzzy ice, which means that we added some extra ice through that event, through the storm passage. Now, if you have a lot of storms and you have regions where preferably you have a frequent occurrence of deformations, such as, for example, along the northern slope of Alaska towards Canada here and kind of like Chukchi Plateau here, in the winter time, from the model simulation, if you calculate or accumulate the total heat released on a monthly basis for March of 1993, we're getting order of about 25 watts per square meter in a monthly mean through those deformations. The heat released in the wintertime when there's no other sources of energy for the atmosphere except the momentum. Now, if you look at the summertime, the numbers are much higher. And then if you go to the eastern Arctic, the story is actually even more interesting because there's an issue that the Atlantic water coming to the ice edge and actually maintaining the ice and marginal ice zone. The black contours here are showing the ice concentration, 15%, 50, and 85%. And you can see that the highest areas of surface heat release are associated with the marginal ice zone and ice edge. So if you can represent the ice edge in the eastern Arctic, and you don't have the warm water advected into that region, you don't necessarily will see that effect. And as a matter of fact, those magnitude monthly mean fluxes clearly will affect your atmosphere. So if you have a fully coupled model, 350 watts per square meter sustained for a monthly mean will definitely have an impact on the atmospheric circulation as well. So you need a fully coupled model for that, because otherwise you will not get the full understanding of how this works. Now, going back a little bit to the oceanography, is if we have the warm water being advected into the Arctic from the Atlantic side and from the Pacific side, there's an issue how well this warm water advected is being represented. And I'm showing here 4 different cases. The upper left is shown here from the fully coupled model with 9 kilometer and 45 vertical layers in the ocean. This is the same model configuration, except that this is not a fully coupled model run. This is the forced model run with your analysis. The lower left is the same as the upper right, except we have 60 vertical levels in that model versus 45. And the lower right, it's 2 kilometers, 45 levels compared to 9 kilometers, 45 levels. And this is a section of Fram Strait between Greenland and Spitsbergen, where majority of warm Atlantic water enters into the eastern Arctic. The warm colors are showing the warmer water, so order of 2 degrees or more, West Spitsbergen current basically coming along the eastern side of Spitsbergen and entering the Arctic. So this is a fully coupled model. This is the 9-kilometer force. This is the 60 level 9-kilometer force, and this is the 2 kilometers. One thing that you can observe easily is that as we increase the vertical or horizontal resolution, we start getting multiple cores of this warm water inflowing to the north into the Arctic. And actually those multiple cores, like this one here, are more closer to what the reality is suggesting, observations, moorings and hydrography for the Fram Strait. So clearly, if we have a coarse resolution, we won't have the details, or maybe not enough even heat and volume flux entering the Arctic compared to a high resolution representation of the model. And as I showed before, in this case, the warm water defines the extent or the marginal ice zone in the eastern Arctic. So amount of heat delivered by this water into the marginal ice zone, into the ice edge, will determine what's going on with the sea ice. So here I'm showing basically calculation of the total heat convergence into the central Arctic through Fram Strait, Northern Barents Sea, Bering Strait, and outflow through the Canary Archipelago. If we add all those heat fluxes, positive and negative heat fluxes, we get the total number, and those numbers here are the 30-year mean heat fluxes into the Arctic. So from the fully coupled simulation, we have about 8 terawatts of heat that enters the Arctic Ocean in a mean net sense that has to be lost to the atmosphere or to melting sea ice. If we go to a force simulation, the same model configuration but force simulation, the number goes to about 13, a significant increase. If we go to a vertical resolution of 60 level with the force model, we're 86% above the fully coupled simulation with the 45 levels. And then if we go to 2 kilometers, the story gets a little more complicated, so there's more work required on that. But what's interesting, if you plot the mean ice thickness from those 4 model runs, it's kind of counterintuitive because the least amount of heat, oceanic heat convergence, somehow is associated with the thinnest ice in the Arctic. So the only thing I can say is that at this point is that there's more story to it than just a direct influence of the oceanic heat convergence. In addition, that some of the ocean heat that enters might be lost very locally at the very entrance. Like, for example, the Atlantic water entering through Fram Strait might be losing a lot of heat just north of Svalbard, not necessarily spreading all over the central Arctic. And by the time the Atlantic water enters the western Arctic, it's deep enough that probably it doesn't have much of the effect on the sea ice cover. But anyway, on the Pacific side, we have another issue, is that we have the warm Pacific summer water coming. This is a profile from the western Arctic. At depth of about 60 to 80 meters, we have the temperature maximum, which is 1-2 degree above freezing temperature. So we have a layer of warm water in the western Arctic sitting about 60-70 meters below the sea ice. And it's available for some action if you can provide that action. And if you can provide some dynamical processes that will entrain this heat from 60 meter depth, you will bring this heat to the mixed layer, to the bottom of the sea ice, including through the winter. So this is not just a summer phenomenon. This profile is a climatological profile. We have warm water sitting at the subsurface in the western Arctic year-round. Now, we have another feature more recently as we started losing sea ice, is that the solar insulation allows the heat to accumulate right below the mixed layer, about 20, 30, 40 meters. And that near surface temperature maximum is another source of heat that might be potentially available for affecting sea ice before freezing or throughout the winter time period. So this is showing like a satellite picture from MODIS for a particular day of August 10, 2007, and the color shading here is representing sea surface temperature. And actually, this is a very interesting figure. You probably have seen, some of you have seen, heard me talking about this. But basically, for me, this is the ocean circulation versus ice albedo effect. The ice has retreated somewhere up here. The color, the dark freezing temperature means that the ice is still melting there, but there's still some ice presence. Okay. The contour here, this is 50%, 25%, and 15%. No, those are bathymetry. The ice is here, those are bathymetry, and you can see the bathymetry representing the Barrow Canyon here. The warm water is coming out along the eastern flank of the Barrow Canyon, as represented by warmer colors, can be up to 10 degrees Celsius warm during the time of August in this particular year. Okay, and as this water exits, this is a vertical section across this line here, you can see that actually it's not flowing continuously, it's actually patches of warm water, and they are not warmest at the surface, they are warmer at subsurface about 10 meters below the surface. So SST from MODIS is maybe not representing the whole picture because much warmer water might be at just 10 meters below. Another aspect is that this is not a continuous flow, so actually those features are representing eddies, mesoscale eddies. So as this coastal current carrying fresh but still very warm water crosses the bathymetry, it becomes baroclinically unstable, starts creating those eddies, and those eddies redistribute this warm water across the slope into the southern Beaufort Sea. And this warm water is part of the Pacific summer water that I shown you on this picture. This contributes to that maximum temperature profile in the Western Arctic. And basically, if you look at the September to September of 2005 through 2006, this is the ITP, ice tether profile drifting in the central Western Arctic, in the central Beaufort Sea. During the January through April, we have a significant amount of very warm water sitting here about 60-meter depth, and actually from the winter, so from the end of the summertime, we also have this additional feature called near surface temperature maximum. Okay? So this warm water is present there in a winter, 60 meters below below the surface. So compared to the Atlantic water, which is sitting at 150 to 200 meters or so, it's much shallower and much easier to be potentially incorporated into the mixed layer to affect the sea ice. So now if you look at the effects of eddies, I'm showing here effect of eddies from the 9-kilometer and 2-kilometer model simulation. That's why we need them. You can see that actually this is the Point Barrow right here. In 9-kilometer, we are missing a maximum of eddy kinetic energy that is present in the 2-kilometer model. Okay, this is the upper ocean, upper 100-meter eddy kinetic energy that is basically represented differently between the two model horizontal resolution. And now I'm showing results from satellite observations where they are basically showing the multi-year ice being affected in March 2012 all the way along the north slope of Alaska up to Point Barrow and so forth and the northern Chukchi Cup. And by September, this whole old ice is gone. This ice, if it's a 3-4-year-old ice, probably it's 3-4 meters thick, roughly. The atmosphere from the top cannot melt this ice by itself. It has to be oceanic contribution, the lateral and the bottom ablation that contributes to that. But in any case, by the time September, this old ice, multi-year ice, is gone. And I'm showing here from the 2-kilometer model results, one of the eddy that's being simulated somewhere in this region, anticyclonic eddy. And if you make a cross section along this line, you can see that due to the anticyclonic motion, the warm water from about 10 meters is entrained into the mixed layer all the way to about 3-4 meters depth. So this water is becoming available in the mixed layer. As it's becoming available in the mixed layer, will affect the bottom ice by basically removing some of the ice thickness from the ice in that region, and that ice will potentially be earlier melting, disappearing in this region when the melt season comes in. So I have to skip a few slides here. There's an effect of the fresh water in the Arctic on the sea ice because freezing temperature is a function of salinity, and by having a Western Arctic accumulating the fresh water, we actually have an impact on the sea ice. I don't have time to show this movie, but if anybody's interested in looking at this movie for a 30-year simulation, you can nicely see kind of like breathing Arctic. And I'm listing here different processes and feedbacks that might be important to eventually get this kind of result. What is the contribution from various factors here? And finally, in terms of the using RASM for prediction, 2016 is the first time we tried that with support from the Office of Naval Research. We provided contribution. We had several ensemble members, still very few, but several. And our contribution was for the monthly mean, about 4 million square kilometers. For the minimum daily, we came up, it was about 3.2 million kilometers square. The actual minimum for September 2006, I believe it was about 4.3. So the monthly mean of RASM prediction was within the uncertainty that we provided with that report, which was plus minus 3 million square kilometers. And then the issue was in that year is that we had to bias correct model results at that time, because between the corrected and the raw model simulations for the initial conditions, we had to remove roughly as much sea ice as the bias correction as we were predicting. So we were not very satisfied with that prediction, because basically you are removing as much information as you're predicting. But I'm happy to report that for 2017, without any bias correction, so this is basically a comparison of the satellite remote sensing with the purple lines and our ice extent and thickness distribution for initial conditions starting in July, and this is our prediction of September 2017. And this is starting in August, prediction of September 2017. Our daily minimum has been predicted based on 28 ensemble members to happen September 19, and the total monthly ice extent we're predicting at 4.35. So probably a little low, but the argument again is that without bias correction, we're probably within uncertainty range that we provided with this forecast. So to finish up, I would argue that we need to have process resolving regional and global climate models to reduce uncertainty, basically first to resolve those processes, which will help us to reduce uncertainty and improve prediction of Arctic climate change at seasonal and longer timescales. I have provided some examples of the importance of oceanic forcing on sea ice, especially on the longer timescales. I have discussed some issues with regard to the optimizing model parameter space, and the example is that you shouldn't be using the same viscosity vis-a-vis convection coefficient that you had for a 100 kilometer resolution as you're using it for 1 kilometer. A very important aspect, in my opinion, is that if we continue using the ice extent as the primary measure of the climate model skills in the Arctic, we're actually not seeing a whole picture. And finally, as we start resolving processes and we look at those feedbacks and try to make sense out of them, we need to have additional observations, because standard observations of core variables such as surface air temperature or temperature salinity in the ocean are not enough. We need to start getting observations and measurements of fluxes through the surface to close those budgets, or at least constrain those budgets. And one good example is a new project or program coming up sometime in a year or two. It's called Mosaic, about drifting icebreaker pole stern in the Arctic for a year. With that, thank you very much.
Even though we had a couple of questions during the talk, and we're now several minutes over, I'll ask that additional questions for Wieslaw come during the break, please. Okay, thanks.
Thank you.